Welcome. We're going to look at a typical acids and base question, which is taken from a worksheet which my grade 12s have, and this is question 7. So, first question is to define a base. So first of all, important thing is we're looking for a base in terms of the Arrhenius theory, which means you can't tell me that it's a proton acceptor because that's the Bronsted-Lowry theory. So what we want here is that it is a base that forms hydroxide ions. So it's a base that forms hydroxide ions. And remember, those are OH minus ions in water. Okay? Straightforward, that's theory. Then it says to explain how a weak base differs from a strong base. Here, this is about dissociation. This is about our definitions of weak and strong. So what we're looking for is that a strong base dissociates completely, okay, in water, while a weak base dissociates. Now here we can also say ionizes because of ammonia only slightly. That's the big thing. Weak acids and bases dissociate or ionize completely. Strong acids and bases ionize almost completely. The thing is the completely here, and they form lots and lots of ions, whereas your weak acids and bases only dissociate or ionize a little bit, so you only have a little bit. You only have a few ions. Then they want the reaction shown, the hydrolysis of sodium hydrogen carbonate in water. Here the big thing is to remember that this sodium ion actually isn't important. Because it comes from the strong base, it would have come from sodium hydroxide, which is a strong base. Its conjugate is then weak. HCO3 will come from H2CO3, which is carbonic acid, which is a very weak acid. As such, its ion desperately wants to react again with the water. So this means this reaction is going to become this. The HCO3 minus ion, which is in solution, is going to react with the water. That's what hydrolysis is about. It actually reacts with the water, sets up an equilibrium, and we end up with H2CO3 in solution again, and OH minus. And the thing here is this now becomes a basic salt because when it dissolves, we create OH minus ions, which mean the pH is going to be quite high. Okay, great. A learner wishes to identify element X in the hydrogen carbonate. They're not telling you that this is sodium hydrogen carbonate. We don't know what X is. To do this, she dissolves 0.4 grams of the XHCO3 in 100 centimeters cubed of water. Great. She then titrates this solution with a 0.2 mole hydrochloric acid solution. Great. Methyl orange is used as an indicator. Now we use methyl orange when we have a strong acid and a weak base. Okay? Strong acid, weak base. So that's already giving me an indication where X should be. It can't be a group 1 metal because that would make it a strong base. Okay? First question is to calculate the pH of the hydrochloric acid ions. Okay, well, oopsie, that's a bad choice. pH is the negative log of the H3O plus ions. HCl has one hydrogen in it, which means that the H3O plus concentration is in a 1-to-1 relationship with the HCl concentration. So that means I know what the H3O concentration is. that makes life much easier for us. So this is the negative log of 0,2, which gives me 0.7. It's HCl. I'm happy with it being such a low pH because I know that it is a strong acid. First question, we're good with. Okay? Second question, give a reason why methyl orange is a suitable indicator in this titration. Well, it's a titration. Did I spell that right? Yes, titration between a strong acid and a weak base. They're really wanting you to know why we use methyl orange. Alright? Now for the fun question. So far we've done okay. Now we get to the question which is more difficult. And they say, at the end point, she finds that 20 centimeters cubed of the acid neutralized all of the hydrogen carbonate solution. So all the hydrogen carbonate solution gets used up. Alright? The balanced equation is given. Here we go. It's balanced. So the first thing they want to know is, well, they want you to identify the element by means of a calculation. What you need to recognize is this is an acid-base reaction. Carbonates are all bases. This is an acid. It gives us carbon dioxide and water. As soon as that happens, it actually makes it quite easy for us because when I look at the information I know, right at the top we had 0.4 grams of that solution and we've got 100 centimeters cubed. So what I know here is this. The mass of my base, let's just do here, the mass of the base they told me was 0.4 grams. The volume that I've got of my base is 100 centimeters cubed. Okay. Of the acid, I know the concentration of the acid, which is 0.2 moles per decimeter cubed. And I know the volume of my acid, which is 20 centimeters cubed. In order to identify X, I really actually need to know the molar mass. Once I know the molar mass, then I can subtract the mass of HC and O3 from it, and that'll give me the molar mass of my unknown. Which means I want to go the route of finding the molar mass of my base. When I look at this, I go, well, I need to know the number of moles. I can find number of moles by using N equals M over M. Then I need to find the number of moles of acid, which we can do without a doubt. Or I can use the fact that C equals N M over V, which means I need to know the mass concentration of my base. This I can do. And it doesn't matter which way around you do this, okay? There's always more than one option. I prefer this way. So if I go number of moles of acid over number of moles of base, concentration, volume, concentration, volume. It's a 1-to-1 relationship, which is great. So it's 1 over 1. My acid was 0.2. Here I don't need to convert to decimeters cubed, though you're welcome to. The volume of my acid was 20. Volume of my base is 100. Okay. So what that means for me is the concentration of my base is 0.04 moles per decimeter cubed. Now I can work out the molar mass. So now I can go, well, concentration is mass over molar mass times volume, 0.04. We know that we had 0.4 grams. Molar mass is what I'm looking for. Now be careful. This volume must be in decimeters cubed now. Okay? So this is 0.1. That means my molar mass is 100 grams per mole. So, if I now say, well, the molar mass of XHCO3 is going to be the molar mass of X plus 1 for the hydrogen plus 12 for the carbon plus 3 times 16. That's all equal to 100. That's plus 61. So the molar mass of X is 39 grams per mole. And then I go look on the periodic table and I see that X is potassium. Alright? But now, I said to you there was another option. What if you don't see that you can use Na over Nb? Okay? Which is perfectly acceptable. So we look at this and we go, just with the information I've got, let's do the want over got root. Okay, so now I'm going to do the want over got root. So here we go. Again, bad choice. The number of moles of my acid, okay, is its concentration times volume. So it's going to be 0,2. Now I have to have it in decimeters cubed, so it's going to be 0,02 because I divide by 1,000, and I get 4 times 10 to the minus 3 moles. Okay? To get the number of moles of my unknown carbonate, I have to take 4 times 10 to the minus 3 times by the mole ratio, so I get 4 times 10 to the minus 3 moles. Number of moles is mass over molar mass. So 4 times 10 to the minus 3 is 0,4 over m. And when I do the division, again, I get 100 grams per mole. And now we finish off the question like we did last time. Okay, so the question gets finished off in exactly the same way we did over here. So I'll just let you see them two together. So this now gets done in exactly the same method. Both are correct. Both will get you the same marks. You need to do whichever way makes the most sense for you.